Hello everyone, welcome back to the fourth lecture of the week 9. In the previous lecture, we had explored Taylor's series and the Taylor series expansion of a given function centered at some point. So, around some point in the neighborhood of that point, I can explore the function value in terms of the infinite, sum of the infinite terms. Now, it is the time to explore the same function or a given function at x equal to 0. So, the value, the point is fixed. Such a series is called Maclaurin series. So, whenever in the Taylor series expansion, if you are putting a equal to 0, it will gives you the Maclaurin series. So, we will look at the structure of the Maclaurin series and their mathematical proof. So, remember this one, what was the Taylor series? The Taylor series was f(x) equal to f of x is equal to the infinite terms f a plus x minus a f dash of a x minus a ka whole square factorial 2 f double dash of a x minus a ka whole cube factorial 3 divided by factorial 3 f triple dash of a and so on, right. The nth term was n minus 1 by n minus 1 ka factorial into f of n minus a into a, right. That was the Taylor series expansion and going on for infinite terms. Now, if I put a equal to 0 here, this will become the Maclaurin series and the whole series is called Maclaurin series. So, the first question is how many terms Maclaurin series contain? Obviously, it has the infinite sum of the infinite terms. So, it has nothing but it is containing infinite terms and it is in a very lucid manner. As you can see, f(x) equal to f(0), x into f dash of 0, x square by factorial to f double dash of 0 and so on by putting a equal to 0 here, right. So, it can be written in a sigma notation. F of x can be written directly to summation of n equal to 0 to infinity f of n 0 divided by factorial n xn, right. So, the formula is very useful to find the Maclaurin series in terms of the infinite terms. So, as we have seen that expansion of sin x about x equal to pi in the previous lecture. Now, we will find out the Maclaurin series. That means, I have to find out sin of x, Taylor series sin of x and putting x is equal to pi. Now, in place of this pi x equal to 0 and that will be our answer, right. So, let f(x) equal to sin x, you have to calculate f dash of x, f dash of x is equal to cos of x, f double dash of x equal to minus sin x and f triple dash of x is equal to minus cos x, f fourth of x equal to sin of x, right, and so on, f fifth of x is equal to cos of x and so on, right. And then the whole this series is repeating and so on. So, according to the Maclaurin series, I can write f(x) equal to f(0) plus x into f(0), x square by factorial 2 f double dash 0, x cube by factorial 3 f triple dash 0 and so on. Put the value of here. So, f of x can be written as a sin of x and this can be written as cos 0, cos 0 is value 1 plus that will be minus x into f dash of 0, f dash of 0 equal to, see here, sin of 0 equal to 0. So, this is 0 minus x square by factorial to f double dash of 0 that is minus 1, right. So, this is 1 and so on. So, ultimately you will find out the formula of sin of x, that was the expansion, and sometime it is called Taylor, a special particular expansion of the sin x according to the Taylor series where we have put it the point x equal to 0. So, such a expansion is called Maclaurin series. According to the Maclaurin series, sin x is nothing but sin x is the sum of the infinite terms using x minus of x cube by factorial 3 plus of x 5 by factorial 5. So, sin of x can be written as x minus of x cube, sin of x can be now written as x minus of x cube by factorial 3 plus of x 5 by factorial 5 minus x7 by factorial 7 plus x9 by factorial 9 and so on. And how many terms in the right hand side you are seeing? You are seeing infinite terms of the function, a function which containing the first term as x, the second term is x cube, x5 and x7. So, as you can see, the exponent of this is also the exponent of these is also the odd integers, and also alternate sign is alternate one, right. So, you can remember this one as a sine of x can be written as x minus of x cube by factorial 3 plus of x5 by factorial 5 minus of x7 by factorial 7 plus of and so on, right. So, that is the idea to do the calculations. So, based on that, can we find the Maclaurin series expansion of cos of x? Answer is very easily to do this. As you can see in the last one that sine of x can be written as x minus of x cube by factorial 3 plus of x5 by factorial 5 minus of x7 by factorial 7 plus of x9 by factorial 9 and so on. So, the cos of x the exponents now become even integers, and the same thing is going on. So, putting all those value you will see the same here. So, here cos of x equal to x0 minus x square by factorial 2 plus x4 by factorial 4 minus x6 by factorial 6 and so on, right. So, that was our calculations. Now, the third question is find the Maclaurin series expansion of tan of x. Tan of x as we had seen for cos x and sin x, right. We are expecting those values in terms of the tan of x. You cannot do something like okay, so tan of x is equal to sin of x by cos of x and so on. No, you will have to go through the Maclaurin series. So, for Maclaurin series we need f dash of x, f double dash of x, f triple dash of x and so on, higher order terms. So, tan x, the first derivative is sec square x, the second derivative is 2 into sec square x into tan of x, the third derivative is 2 sec power 4 sec square x tan of x, tan square of x and so on. So, according to Maclaurin series, f x can be written as now f0 plus x into f dash of 0, x square by factorial 2 f double dash of 0, x cube by factorial 3 f triple dash of 0 and so on, right. So, f0 equal to tan 0, that is equal to 0, f dash 0 equal to sec square 0 equal to 1, f double dash 0 equal to 2 sec square 0 tan 0 is equal to 0 and f triple dash calculated as 2. So, now the derivative is going on, it is not going to stop here. F fourth of 0 can be calculated, f fifth of 0 can be calculated. Putting all these values in the equation 1, we get tan of x equal to 0 plus x1 x square factorial t into 0 and so on. So, this will be going to be 0 and then tan of x can be written in a very simpler form as x plus of x cube by 3 2 into x power 5 by 15 and so on. So, that is sine of x, cos of x. Sine of x was what? X minus of x cube by factorial 3 plus of x to the power 5 by factorial 5 minus so on. Cos of x was what? 1 minus of x square by factorial 2 plus of x to the power 4 by factorial 4 and so on, right. And now, you can see here tan of x equal to x minus plus of x cube by 3 plus of twice into x to the power 5 by 15 and going on, right. Similarly, can we find the Maclaurin series expansion of sine hyperbolic of x? To do this, we need the higher derivative of sine hyperbolic of x. The first derivative of sine hyperbolic of x can be written as cos hyperbolic of x. The second derivative is sine hyperbolic of x and so on. Cos hyperbolic of x, sine hyperbolic of x. So, alternate is going to be the same one, right. So, according to the Maclaurin series, fx can be approximated and can be written as the sum of the infinite terms as fx equal to f0 x into f dash 0 x square by factorial 2 f double dash 0 plus x cube by factorial 3 f triple dash 0 and so on, right. Put all these values here. You will get f0 equal to 0, f dash of 0 is equal to 1, f double dash of 0 equal to 0, f triple dash of 0 equal to 1 and so on. So, it is going to be alternate one 0 1 0 1 0 1 and so on. So, sine hyperbolic of x can be written as 0 plus x square by factorial t into 0 x cube, and so just the even positions terms is going to be 0 only. So, only written for odd positions. So, sine hyperbolic x can be is equal to x plus of x cube by factorial 3, x 5 by factorial 5, x 7 by factorial 7 and so on, right. So, the question arises that can we find out cos hyperbolic of x? Answer is in a very lucid manner that yes, we can easily find out of cos hyperbolic of x. So, for cos hyperbolic of x, we have to find out the derivatives. So, these derivatives are also the alternate derivative. As you can see, the first derivative of cos hyperbolic is sine hyperbolic of that one, that means the second derivative is cos hyperbolic, and again it is going to be sine hyperbolic, again it is going to be cos hyperbolic. So, it is just a alternating thing, and use the Maclaurin series formula, that is f0 plus x into f dash of 0 plus x square by factorial 2 f double dash 0 x cube by factorial 3 f triple dash of 0 and so on. You will find out f0 as equal to 1, then f dash 0 equal to 0, then f double dash 0 equal to 1, f triple dash 0 is equal to 1, f fourth of 0 is equal to 1, f fifth of 0 equal to 0 and so on. So, it is alternate one. So, cos hyperbolic of x become 1, then these terms, the even positions terms are going to be 0 and only written as the odd positions one. So, this will become cos x equal to 1 plus x square by factorial 2 plus x 4 by factorial 4 x 6 by factorial 6. Now, you can compare your result and you will easily see that how they are completing each other. So, sine hyperbolic x here is equal to x plus of x cube by factorial 3 plus of x 5 by factorial 5 plus x 7 by factorial 7 and so on, while cos hyperbolic of x is equal to 1 plus of x square by 2 plus of x square by factorial 2 plus x 4 by factorial 4 plus x 6 by factorial 6 and so on. So, it is very easy to remember all those formula using the Maclaurin series. So, I think we have justified our problems. Can we try for a tan hyperbolic of x? So, assignment for you, the first assignment, find Maclaurin series expansion of tan hyperbolic x. Maclaurin series always give you around x equal to 0. So, sometime it is also used for getting a approximation functions of a general terms. So, its neighborhood is nothing but it is the neighborhood around x equal to 0. So, that is why sometime you are just using f of x here. So, in terms of a general term, f x can be written as f0 x f dash 0 x square by factorial 2 and so on. This will give you approximate function value around 0. So, sometime it is quite useful, and we had find out sin x, cos x, tan x, and then sine hyperbolic x, cos hyperbolic x, and then these are the examples we had already done, and your assignment for this this PPT or this lecture is find out cot of x, then tan hyperbolic of x, and then cot hyperbolic of x, and also use this formula to find out sec of x, right. So, these four are also important. So, find out the Maclaurin series for these four trigonometrical functions, and then you will see that these expansions are quite useful for further problems. So, we had seen Maclaurin series as well as the some problems using the Maclaurin series, and in particular we had derived this Maclaurin series formula or expansion from the Taylor series, but I have not given you how to prove this one. Proof is in one line. You just put a equal to 0, as we had already done this, right. So, let me give you at here how we going to take this one from Taylor series to Maclaurin series. So, write down f of x, and you are finding a function f of x here, and x equal to a is given here in the neighborhood n of a, right. So, f of x n equal to 0 to infinity f n n and factorial n x minus a p power n, right. That was the Taylor series expansion, and how we had proved? We had proved that let f of x, so its proof was using f of x equal to p n x of and r n x of x, right. R n x is nothing but these are the remainder terms after nth term, right, after the nth term, and this p n x, then this p n x is the polynomial, and we make this p n x as the sequence of the nth polynomial. So, this is treated as the sequence of the nth partial sums of f of x, right, and if it is going to be f of x, then the whole this right hand side is going to be f of x. So, that is how we had approximated. So, now the foremost question was that if a equal to 0, putting a equal to 0, this f of x is approximated as a very easy thing. So, f of n a divided by factorial of a, now it has become f n of 0 and this will become x n, right. So, this was become Maclaurin series, this become Maclaurin's one, Maclaurin series, right. But if you are in geometrical sense, if you are looking for a geometrical sense, then you can look like this. So, let us say this is the function and this is the f x, and I want to approximate this function with the polynomials. These are the polynomials. What are these? These are the polynomials. These are the polynomials of nth degree or first degree, second degree, third degree, fourth degree and nth degree, right. So, these are the polynomials in the right hand side, and here it is the function only. So, for a given function f x here in the red line, how we can approximate by first order and second order polynomial only, and that is this is the first order polynomial, this may be a second order polynomial, this may be a third order polynomial and so on. So, that is the polynomial for a particular point. Now, believe it that this point is origin itself, x equal to 0 itself. That is the huge helpful for Maclaurin series. So, Maclaurin series is useful to finding out approximation of a given function in the neighborhood of origin x equal to 0 itself, and that is why as you can see the proof is quite easily, and henceforth it has been left here, right. So, you can go through the proof and you can find out the Maclaurin series of any given function. For sin x we had seen that it containing only the odd exponent terms. See here, this is the odd degree terms. Similarly, you can have find cos x is the only even exponents 1, and then tan of x, as you can see here, this is the combinations of the odd one. So, x to the power 1, x cube by 3 plus of 2i's by 15 x to the power 5 and so on. Then sine hyperbolic is also a very useful one, and it containing only the plus sign as well as the odd exponent terms, x plus x cube by factorial 3x5 by factorial 5 and so on. Similarly, cos hyperbolic is also good one, and it will become only containing the terms as the even exponents terms. 1 plus 1 can be written as x to the power 0. So, x 0, x square by factorial 2, x 4 by factorial 4 and so on. So, that is some of the terms. Maybe we can find out e to the power x. So, exponent of that one. For the Maclaurin series, exponents is quite easy. 1 plus of x square by 2 factorial 2 plus of x cube by factorial 3 plus of so on. Can you find it? Obviously, we can find out. So, let us say f of x equal to ex, f dash of x is equal to how much? Ex, f double dash of x is equal to ex and so on. So, now f of 0 equal to e to the power 0 is equal to 1. This will become also 1. This will become all the terms containing this derivative becomes 0. So, what will be the, as you can remember, Maclaurin series? Maclaurin series is f of x can be written as f of 0 plus of x into f dash of 0 plus x square by factorial 2 f double dash of 0 plus x cube by factorial 3 f triple dash of 0 and plus so on. So, now put the value f 0 is equal to 1 plus of x into 1 plus of x square by factorial 2 plus x cube by factorial 3 and so on. So, this is the proof for Maclaurin series of f x equal to e x, f x equal to e x. So, as now you can see that exponential function can be approximated by the sum of the polynomials of a given order, and that is how Maclaurin series play a significant role in shaping the whole function and its derivative nearby. So, I believe that it will give you the more and more concepts about the Maclaurin series and how to find the Maclaurin series expansion of a given function. So, thank you so much.